Welcome to this microlecture on regression analysis where we will walk through the key steps of building, checking and applying regression models. Let's dive in. The first step is to choose a model that describes the relationship between the inputs and the output. If the data shows a straight line relationship, we use linear regression. If not, we consider nonlinear regression, which handle curves or changing effects depending on the input level. When building a regression model, one of the first decisions we face is how to define the shape of the relationship between the variables. While linear regression is often a good starting point, it doesn't always capture a complexity in the data. So how we know whether a straight line is enough or whether we need to curve it with polynomial terms? Instead of relying on a single test, we run a combination of visual diagnostic, statistical comparison, and theoretical reasoning. For example, if a scatter plot of your data or the residual reveals a clear curve or pattern, that's a strong hint that linearity might not hold. Similarly, if a polynomial model explains significantly more variance with only a small increase in complexity, it might be worth using. It's also important to think about context. Does the curve relationships make sense for your data and your domain? Statistical tools can point us in the right direction, but they are most powerful when combined with subject matter knowledge and careful interpretation. Once we've built our regression model, the next step is to assess how well it actually performs. In other words, does our model truly explain the variability in the outcome variable? And are all our predictors meaningfully contributing to that explanation? We usually start by looking at the coefficient of determination, or R-squared, which tells us what proportion of the variance in the response variability is explained by our model. A higher R-squared generally indicates a better fit, but we should be cautious. A high R-squared doesn't always mean the model is good, especially if it's overly complex or includes irrelevant predictors. To dig deeper, we examine individual coefficients and their p-values, which help us determine whether each predictor has a statistically significant impact on the response. It's not just about whether the overall model works. It's also about how much each variable contributes to the story. Finally, we should compare models when appropriate, either by using adjusted R-squared, AIC or BIC, or cross-validation, to ensure we are not just explaining noise. Good modeling is as much about critical evaluation as it is about estimation. Here is a practical example. A sales manager at a merging company wants to know whether advertising costs influence turnover. We have data on turnover and a budget, which we can use to build a regression model. We start by choosing a simple linear regression model, as shown on the slide, where X represents the amount spent on advertising per year. The actual observed value, yi, consists of two parts. The part explained by the model, which is b0 plus b1 xi, and the residuals ei, which captures the variation not explained by the model. Looking at the regression output, we see that the coefficient for advertising b1 is approximately 0.75. This means that each additional unit of advertising, the quantity sold increased by 0.75 units. The R-squared values is 0.82, indicating that the model explains about 83 of the variability in sales. This suggests a strong relationship between advertising and margin sales. After estimating the regression function, we evaluate how well the model explains the variation in sales. One key measure is the coefficient of determination, R squared, shown here as 0.82. This means that about 83% of the variability in margin sales is explained by advertising. The formula for R squared compares the variation explained by the model to the total variation in the data. A higher value indicates a better fit. The standard error, denoted by S, tells us how much the observed data deviate from the predicted values and average. To improve the model, we added a dummy variable. This captures whether the advertising budget is above or below the median. A dummy variable lets us check, if possible, nonlinear effects, for example, if only large advertising budgets boost sales. If you would like to learn more about how dummy variables works and how to interpret them, we will cover that in another microlecture titled Advanced Concept in Linear Regression, Assumption, Dummy Variables and Interactions. Now let's assess the quality of our regression model. The R-squared value is 93%, which means the model explains a large proportion of the variance in the dependent variable. The adjusted R-squared, which accounts for the number of predictors, is also high at 87%. The residual variance and standard deviation reflects the average error in prediction. We also use statistical tests to validate the model. The F-test checks whether the predictor has statistically significant effect. Since the test statistics exceed the critical values and multiple significance level, we reject the null hypothesis, meaning the predictor is indeed relevant. The Ramsey reset test examines whether the model is correctly specified. In this case, we do not reject the null hypothesis, suggesting that the model form is appropriate and no key variables are missing. Overall, this result indicates that the model is statistically well specified. This correlation plot helps us explore linear association between variables and in the dataset. The high valued here, R equals 0.91, indicates a strong positive linear relationship between advertising and the quantity of margin sold. This suggests that as advertising increases, sales tend to increase as well. Such a strong correlation supports our earlier regression findings and is consistent with the idea that advertising may be a key predictor in this context. However, it's important to note that correlation alone does not imply causation. This scatter plot displays the relationship between advertising cost and quantity sold. The trend line represents our linear regression model with its equation shown above. According to the model, each additional unit spent on advertising is associated with an estimated increase of approximately 0.75 unit in sales. The R-squared value of 0.83 indicates that the model explains about 83% of variability in sales, suggesting a strong linear fit. The residuum or residual is the difference between what our model predicts and what happened. Analyzing residuals tells us how well our model fits each data point. In the top left plot, we see how these residuals vary across observation. Most values fall within ±3 standard deviation, indicating no major outliers. The QQ plot compares the residual distribution to a normal distribution. Since most points align with the red line, the residuals appear approximately normal. The bottom right plot shows residuals versus predicted values. The lack of a clear pattern suggests constant variance or homoscedasticity. Altogether, this diagnostic supports our model provides a good fit to the data. Regression isn't just about understanding the past. We want to predict future outcomes. Say, we plan to spend 1,400 on advertising. What turnover should we expect? According to the model, we predicted quantity is about 2089 units. But regression doesn't stop at a single estimate. It also let us define a confidence interval, shown here in yellow, around this predictor. This interval gives us a realistic range where we expect the sales to fall, helping us account for uncertainty and make better informed decisions. Keep in mind that this prediction and the confidence level are only valid if the assumptions of the regression models are met. This includes linearity between variables, constant variables of residuals, known as homoscedasticity, independence of observation, and normally distributed errors. If you are interested in learning more about these assumptions and how to check them in practice, we will explore them in detail in the microlecture titled Advanced Concepts in Linear Regression, Assumptions, Dummy Variables, and Interaction. Thanks for joining this microlecture on regression analysis. We hope it gave you a clear view of how to build, assess, and apply regression models in practice.